Hello, my name is Brian Shuve, and I'm on the physics faculty at Harvey Mudd College, which is an undergraduate college in the Los Angeles area. And I'm going to be talking about some of our recent work on baryogenesis from dark matter freeze-in. So the motivation for our scenario comes from trying to address the problems of dark matter and the baryon asymmetry. And both of these phenomena rely on or suggest that there are dynamics that are out of equilibrium. In the case of dark matter, we know that it's cold um, and that it has to be out of equilibrium now and likely deviated from equilibrium at some point in the universe's history. And for the matter-antimatter asymmetry, we also know that if uh, the system were always in equilibrium, you could never generate an asymmetry in the first place, or any pre-existing asymmetry would be eliminated so that we would have an equal number of both. The natural question that we might ask is, could these two phenomena be relying on the same out of equilibrium physics? And this might allow us to narrow down or suggest some phenomenological directions. The answer, of course, is yes, and that's what I'll be talking about for the rest of this talk. So the scenario that's promising for bringing these two out of equilibrium conditions together is the mechanism of freeze-in dark matter. And just as a brief review, this is in some sense conceptually the simplest explanation of the dark matter abundance. Dark matter is always out of equilibrium with standard model particles and is produced very slowly. And all you do over time is integrate the total number of collisions that produce dark matter. At some point, the production becomes kinematically suppressed and you flatten out to the current co-moving density. And higher dark matter production rates therefore imply higher number densities today. So for example, a very simple and commonly studied model of freeze-in dark matter has some new BSM particle like a scalar, which carries standard model charges, and it can decay to, say, a standard model lepton and a dark matter particle. And there's some dimensionless coupling F that determines the strength. And we can calculate the abundance today, and we see that it matches the observed dark matter density for, say, couplings of about 10 to the minus 8 if your dark matter is at the 10 keV scale and this BSM particle has a mass at a TeV. And this is promising for a few reasons, because this is a mass range that we can potentially test with colliders like the LHC. And this is a mass range is interesting because dark matter could be warm in that scenario and have some potentially interesting cosmological signatures. But as you'll see, the dark matter abundance alone only depends on the product of these factors. And so we could, for instance, make the BSM particle 1,000 times heavier, which would make it unobservable at collider experiments. And that would also make the dark matter 1,000 times heavier and turn off those cosmological signals. So this freeze-in dark matter scenario could be promising, but it's not a guarantee for discovery in any of the types of searches that we're doing now. So what we're interested in is, can we use this extended period of out of equilibrium nature of dark matter to generate a baryon asymmetry? And the answer is yes, if you have two or more dark matter particles, which means that the decay of this BSM particle could produce a superposition of dark matter particles. And I'll talk through how that works, but essentially the asymmetry is generated in the annihilation of dark matter particles that have been previously produced in the decay. And what we find is that it works kind of out of the box, that parameters people consider for freezing dark matter just work for baryon asymmetry. But in this scenario, most of the viable parameter space does have some kind of experimentally detectable signature. And this associated standard model particle could be a lepton, quark, or even a Higgs field. But it does have to be a standard model particle because we're generating an asymmetry in standard model field through this coupling. So to talk through how this works, this mechanism is related to, if you're familiar with the so-called ARS leptogenesis or net leptogenesis through sterile neutrino oscillations. But in this case, the oscillating states are dark matter. So it's easiest to see how this mechanism works if instead of having one BSM particle, we have two. We'll call phi1 and phi2, where phi2 is the heavier one. And just for illustration, we'll pick the couplings to maximize the asymmetry. So what we're showing here, for instance, is that the phi1 decays to an electron, and this linear combination of dark matter chi1 plus chi2, the antiparticle phi1 bar will decay to chi1 bar plus chi2 bar. For the couplings of phi2, we'll choose a kind of maximally orthogonal set of states with a relative phase, chi1 minus I chi2, and the anti-dark matter state will therefore be chi1 bar plus I chi2 bar. And what we can now do is track the production, evolution, and subsequent rescattering of dark matter states. So let's say I have phi2, which decays to an electron and this linear combination, and the antiparticle decays to a positron plus the linear combination with the complex conjugate. Because the state is out of equilibrium, this dark matter state is produced coherently and just propagates according to time evolution, like you would expect with just with the Schrodinger equation. And crucially, it's the same phase that shows up in the time evolution phase, the same sign. And so we can consider, for instance, what happens if this phase represents a pi/2 oscillation. And what we see is that this top state is oscillated into chi1 minus chi2, and the bottom one into chi1 bar plus chi2 bar. And this is the effect of CP violation. So this is the parity violation at home part, I guess, where you get different behaviors between particles and antiparticles. Now, if you go back to what we showed here, it's the chi1 plus chi2 state that couples to chi1. And so what we find is that at this moment in time, this antiparticle, your positron, can go into phi1 bar, but the top state is blocked. And so what we'll see at this moment in time is that you're depleting the positrons more than the electrons, so you're going to generate positive electron asymmetry. This is how you can generate particle-antiparticle asymmetries through this mechanism. Now, you might have some questions like, why did you start with phi2 and not with phi1? And in fact, if you do the opposite, you'll find that in starting with phi1, the particle process can proceed, but the antiparticle process is blocked. Okay, and in that case, you might think, well, these processes will just cancel when I sum over them. But if this phi2 particle is much heavier than phi1, such that at this moment in time when these particles are oscillating, phi2 is much heavier than the thermal energy in the bath, then this will actually be kinematically suppressed and there will be no scattering into phi2. So the expansion of the universe can actually lead to the production of particle-antiparticle asymmetries through a combination of decay, oscillation, and then scattering. If you want to look at more details, we give a pretty clear outline of this in our papers. And also, like I said, it has similarities to air astrophysical case. Now, you might think, well, this is after pi/2 oscillation. What about 3 pi/2? Well, the opposite will be true. But because the universe is expanding, even though the oscillation is a sine function, when I integrate, the rates are not constant. And so what we'll end up with is an asymmetry that does not integrate to 0. The last thing that we need to think about is the fact that if we go back to a process like this, in the lower process, I'm depleting the positrons more than the electrons, so I generate an asymmetry of more electrons and positrons, but I'm also going to have more phi1 bars kicking around than phi1s. And what this essentially says is that these phi1s and phi2s can carry lepton number. And so the asymmetry that we've accumulated in leptons can be canceled by the asymmetry that's stored in these new particles. So the worry is that when they decay, they're going to wipe out the asymmetry that we have preciously generated in standard model fermions. So the way that you can still generate an asymmetry in this model is that baryon and lepton numbers are coupled in the standard model through sphalerons, that it's really B minus L that's preserved, but B plus L is violated. And what that means is that I have an asymmetry in phi, and then I have an asymmetry in standard model leptons, but some of that bleeds over into the baryons. Okay. Now, this is true in the unbroken electroweak phase, but at lower temperatures, the baryon and lepton numbers become sequestered from one another. So if I can keep some of the phis around to this time, then when they decay away, I still have some sequestered baryon number, and essentially I'm safe. So what we discover is that provided these scalars live long enough so that they survive down to the electroweak phase transition, you can generate a baryon asymmetry and everything works out. There's a lot of moving parts here, but what I want to emphasize is that the ingredients here are very minimal, and this is just the dynamics that you get for this particular Lagrangian. So even though there's some interesting dynamics, that just comes from the couplings in this very simple setup. So to show that this kind of physical example actually leads to viable baryogenesis, I'm showing you some numerical results. And on the left, so this is again in the case of 2 mediators, we're making the phi2 quite heavy, and we're showing the phi1 mass as a function of its lifetime. And these contours show the region with successful baryogenesis. And we see that for dark matter masses in the range that I mentioned earlier, you can get baryogenesis to work. There are various phases and mixing angles in the Yukawa couplings, and all this is showing is that you sort of don't really have to have any special alignment to make it work. What we do have here is a massless lighter dark matter particle, and what matters to the asymmetry generation is actually the mass splitting be related to the oscillation time. So the asymmetry does not depend on the dark matter masses, but the dark matter abundance does. And so essentially, if I make my lighter dark matter state heavier, then I don't enhance my asymmetry, but I do enhance my dark matter abundance, and that actually leads to a narrower parameter space. So here, for instance, instead of having a massless chi1, I have the mass equal to chi2 over 2, and you see that the viable parameter space shrinks, but it's still non-zero. And so what we see is that indeed for masses that are of the new particles accessible at the LHC and lifetimes that are sort of interest in terms of phenomenology, we can get viable dark matter and baryogenesis. But it's also a closed parameter space. I can't actually just make everything heavy and decouple it. And so we're pushed into this regime where we potentially have interesting signals. Now that's with two BSM states. Turns out you can actually get it to work with even a single one. And in this case, you no longer get an asymmetry in 5 versus 5 bar number densities. But what you can do is essentially accumulate differences in rates like the ones shown here, where this rate here produces an electron and absorbs a muon. The process on the right creates a positron and absorbs an anti-muon, and I can get asymmetries in positrons versus electrons and anti-muons versus muons that when I sum over them, I get 0, but the asymmetries are nonetheless there in the individual lepton flavors. So this does not give us a baryon asymmetry on its own, but it can subsequently source a further baryon asymmetry in one of two ways. In the first one, we just have the minimal setup, and basically, after you generate the asymmetries in the lepton flavors, this scalar can undergo further decays, and the Pauli blocking from the fermions will differ based on if it's a particle or antiparticle, depending on whether it's electron, muon, or whatnot. And so you can accumulate net asymmetries in lepton number by essentially having flavor-dependent decay rates and taking into account Pauli blocking. The other possibility is that this scalar could have additional couplings with nanomonoparticles that are not related to dark matter, which explicitly violates lepton number. And then actually you don't have to worry about this situation that I was telling you about where there's lepton number stored in the scalar because you're explicitly violating it. And here you generically do get a much larger asymmetry. So in this minimal model, it turns out you can get it to work. I'll show you a couple of numerical results. And in a paper that just came out this year, we even showed that you could get dark matter and baryogenesis to work even if this scalar were heavier than the reheat temperature, so that it's only mediating 2-to-2 scattering and not decay, although it's a somewhat limited parameter space in that scenario. So just to give you a sense of the parameter space, this on the plot here, we're showing the ratio of the observed baryon asymmetry, the baryon asymmetry you can generate to the observed one. And you see that it's possible to generate the observed one for scalar masses up to about a TeV, but it is quite a constrained parameter space here. And typically you need larger couplings and therefore shorter lifetimes, just because you require this extra decay step, which you want a relatively large decay rate in that case. In the case of lepton number violation, we can get orders of magnitude enhancements over the minimal model because you're explicitly violating lepton number. And so we see that if you increase this lepton number violating coupling, you can get a factor of 100 increase in the asymmetry. All right, so what's interesting about this is that the dark matter and baryogenesis picture works out of the box for ranges of parameters that are already of interest. And what we find in terms of phenomenological predictions is that we, for instance, in the case of IR free ZAM, where you are physically producing this scalar particle on shell, its mass has to be at the TeV scalar below, and your dark matter masses are in the 10 to 100 keV range. And that's interesting because we can potentially have a variety of different probes from colliders, rare decay, searches like for muon decays to flavor violating decays. You can also, the fact that you have these warm dark matter components can alter small scale structure and be tested. And in the scenarios where you explicitly violate lepton number, you actually induce dark matter decay, which could be detected in X-ray lines. So to spend a minute or two on each of these. So for structure formation, this is just the observation that if dark matter is relativistic at late times, it can free stream and wash out small scale structures. And so in this model, we're producing dark matter in the decays of or scattering of some BSM particle above the electroweak scale. And so we can compute the linear matter power spectrum and look for where it cuts off and compare it to warm dark matter models. So this actually has both a warm dark matter curve and our model, and you see that they agree very closely, so we can map the warm dark matter bounds. And what we find are that the bounds on a heavier dark matter state are somewhere in the 15 to 25 keV range for IR freezing when phi is decaying, and 25 to 40 keV for UV freezing. So there's still viable parameter space, but it is eating into the parameter space that's relevant for baryogenesis. And what's interesting, as I mentioned, is that you can have these scenarios where you essentially have a dark radiation component where your lightest dark matter state is effectively massless, so it's not contributing to the dark matter energy density now, but it does contribute in terms of oscillations. And so we can have sort of warm multi-component dark matter models that might even have stronger constraints than the ones that are above. So that's something that we're looking at that we think could be interesting, that may be giving different effects on small scale structure. In terms of X-ray lines, as I mentioned, that if you have explicit lepton number violation, you can have dark matter decaying to a photon and a neutrino, essentially because you're violating lepton number, and you can get monochromatic X-rays. And in a lot of the interesting parameter space, we can calculate what this rate is. Over here, we're showing, again, the blue contours are the baryon asymmetry you can achieve over the observed one as a function of the scalar mass and some couplings. And what we see is that at lower scalar masses, we need the lepton number violating coupling to be on the smaller side in order to avoid having these decays. So the current status of this is our model doesn't conflict with observations, but it could be seen, and improvements would test interesting parameter space. Finally, collider searches, these scalars can decay to lepton plus dark matter, and these look a lot like supersymmetric particles called leptons at particle colliders. But what's interesting is that this scalar could decay not just all of the 100% time to electrons, but actually is motivated to decay some fraction of time to electrons, some fraction of time to muons, and some fraction of time to taus. And we can map out the constraints as a function of the mass and lifetime. And typically, as you have it decay to more different types of leptons, you weaken the constraints. And this is, in some sense, the most challenging benchmark if it decays a quarter and a half to each of these 3 lepton flavors. There's only a narrow range of these phi masses that are ruled out at the LHC, and you could actually have them as light as about 100 GeV and not have been seen before. And it's very interesting because the naive limits are up at about 500 GeV, but there's this huge open parameter space. So we did a collider study to see, if you could squeeze out some extra sensitivity at these lower masses where you have larger backgrounds, but also larger signal rates. And we did seem to find that you could get a reasonable improvement in the significance and consequently, the luminosity you'd need for exclusion at the 2 sigma level, which would suggest that you could significantly expand the range of sensitivity of current collider studies. So hopefully I've given you a little bit of a taste of why simple freeze and extension of the standard model can give rise to some very interesting CP violating dynamics in the early universe, and that this might actually explain why we're here and in a way that we could test. So I want to thank my amazing undergraduate students, many of whom worked on papers that were related to this project or are currently in my group working on follow-ups or other related topics. So I look forward to the discussion. Thanks for listening.